Alright, let's get started with Lesson 3, Enthalpy. This Lesson 3 really focuses on the relationship between heat energy and the potential energy of a system. So to begin with, let's look at potential energy a little bit closer and how potential energy relates to the stability of a system. So essentially, we understand that potential energy is stored in chemical bonds because of the electrostatic or coulombic attractions or repulsions between the charged particles. Now, the stronger the electrostatic attractions between charged particles, the lower the potential energy and the more stable the system is. Now, why is this statement so important? What it tells us is that nature favors lower potential energy systems. In fact, the lower the potential energy of a system, the more stable that system will be overall. And so the stronger the electrostatic attractions are, it will lower the potential energy, creating a more stable system. That's what this is trying to say. That's a very important concept to understand. So again, I'm going to repeat that one more time. The lower the potential energy of the system, the more stable that system will be. Alright, this will introduce a new term, enthalpy. The symbol of enthalpy is H. Alright, now enthalpy can often get mistaken quite a bit and a misunderstanding concept by first-year students. Enthalpy is critical to understand here. And so let's take this very slowly. When the system is under constant pressure, okay, constant pressure, the total potential energy in the bonds and in the intermolecular forces of the substance is known as the system's enthalpy. Okay, so essentially what we're saying is the total potential energy of a system is known as its enthalpy, as long as the pressure on the system is constant. And this is really the typical case of most chemical reactions or processes. The atmospheric pressure is going to be constant, and therefore the potential energy of a system is known as the enthalpy. Now, we can then equate this that enthalpy is equal to the total potential energy of the system at a constant pressure. Now, the total enthalpy of the system cannot be measured. So you can't measure all the enthalpy, and we've talked about that. You can't measure the total amount of potential energy or kinetic energy in that fact. So therefore, we cannot know the total enthalpy of the system. But what can be measured is the heat absorbed or released during a physical or chemical reaction. Now, this means then that we can relate the change in heat energy to a term that we call the change in enthalpy, which is delta H. All right? Now, why can we relate this? Simply because if the change in enthalpy, which is really the change in potential energy of the system, is equal to the amount of heat lost or gained by the system because of the first law of thermodynamics. So this means that for a reaction studied at constant pressure, the flow of heat is a measure of the change in enthalpy for the system, or in other words, the change in potential energy. So for this reason, the terms heat of reaction and change in enthalpy are used interchangeably for reactions studied at constant pressure. Okay, so we'll dive into this a little bit more and get into some better understanding, I think, of enthalpy throughout this lesson. Alright, so let's define change in enthalpy. Again, the change in enthalpy is delta H. The change in enthalpy is the potential, or the change in potential energy of the system during a chemical or physical change under constant pressure. Therefore, the change in enthalpy of the system is equal to the change in heat of the system because of the first law of thermodynamics, which we explained earlier. So that means this equation right here, the change in delta H of the reaction is equal to the change in heat of the reaction, all to do with the first law of thermodynamics, which means that energy is conserved. So what we're bottom line is, this is what we're saying, is that if a reaction releases heat energy, then the potential energy of the system must also be changed. And so if we're losing heat energy, then we're also losing potential energy, because the potential energy is converted into heat energy and leaves the system. So when we say that one more time, because I think that's absolutely critical. During the course of a chemical reaction, if heat energy is lost by the system, that tells us that the potential energy of the system is being reduced. It has also been lost. And lost in the fact that the potential energy was converted into heat energy and transferred out of the system into the surrounding environment. And that's what we're indicating by this equation right there. Alright, so during a chemical reaction then, energy is required to break chemical bonds. In the reactants, an energy is released when new bonds are formed in the products. As a result, bond breaking and bond forming, there is a change in the potential energy of the system. Alright, so enthalpy changes depends on the bonds in the product. If the products are stronger than in the bonds in the reactants. So what we're saying is that during the course of a reaction, we're going to be breaking and forming new bonds. And breaking bonds, when we break bonds, it requires heat energy to break those. All right? And when we form new bonds, energy is released as heat energy. And so because of that, when we form new bonds and heat energy is released, then there's going to be that change in potential energy or enthalpy of the system. This leads us to two very important vocabulary words that we need to have a discussion on. First is exothermic processes or reactions. Essentially, exothermic means that the process is going to release heat energy during a chemical or physical change. The word exo means to leave or to exit, and thermic means energy. So we're talking about the exiting of heat energy from the system, the reaction system or reaction mixture. So this results in a decrease in potential energy of the system, which then makes the sign for delta H a negative, because there's a loss in potential energy of the system. Not that there's a negative potential energy. Again, it just tells us direction, that the potential energy is being converted into heat energy, and heat energy is lost from the system during an exothermic process. All right? Now, endothermic reactions. The process is an endothermic reaction if heat energy is being absorbed during the chemical reaction or change or physical change. This results in an increase in potential of the system. Therefore, the delta H value is positive, because there's going to be an increase in potential energy on the system. All right. So the terms exo and endothermic are quite important to our understanding of thermodynamics. Exo, we release heat energy, and the potential energy goes down. Endothermic, we absorb heat energy, and the potential energy goes up in the system. Okay? Alright, so here we're going to demonstrate a reaction, kind of a theoretical reaction system that's going on here. So in the beaker, we are going to have a reaction mixture, and so we're going to have reaction mixture. Alright, And this reaction mixture, we're just going to kind of put a little, I don't know, little compartmentalized idea that it's a reaction mixture. And the reaction mixture is going to be in a matrix of water. So we have water that the reactants are in. So in other words, all the reactants are placed or surrounded by water. Now we're going to put a thermometer into the water, and the thermometer is going to read, let's say, 25 degrees Celsius. All right. Now, that's going to be what is known as the starting temperature. Starting temp. Okay. Now, once that reaction mixture is all mixed together, a reaction is going to occur, which is indicated by the arrow. Reaction occurs, and in the end we form our products. Let me actually erase that and write that a little bit better. So products. Alright, and of course we have our thermometer that's in our water still, water matrix, and the temperature now reads 75 degrees C. Right? So during the course of the reaction, the temperature of the water, remember the thermometer is measuring the temperature of the water, not the reaction mixture. Okay? Not this product and reaction mixture, only the water. So it tells us that the water's temperature initially started at 25 degrees C, and then after the reaction, the water temperature now is started at 25 and now it is 75. So we have a final temperature of 75. Okay? So what does that mean exactly? Well, essentially, the water and the thermometer are acting like the surroundings here. The system is the reaction mixture. All right? So you got to understand that. The system is the reaction mixture, as we've talked about before. So the water, the thermometer, the beaker, and everything else is the surrounding environment. So what had occurred here then is that the surrounding environment must have gained energy for the temperature to go up in the water. So what happened here was the reaction mixture released energy into the surrounding environment. Okay? So heat is being released. So essentially, we could say that delta Q, which is heat, is negative here. Well, if it's a negative delta Q, what kind of reaction is this? Exo or endo? Well, it's got to be exothermic. Okay, it's got to be an exothermic reaction because delta G, or the delta Q of the reaction, the heat, is being lost from the system and going into the surrounding, which is causing the temperature of the surrounding environment to go up. So this is a great example of an exothermic reaction. Now, in terms of potential energy, what's occurring here is that the reaction mixture is losing potential energy because this is an exothermic. Remember, during an exothermic reaction, potential energy is lost, which is really enthalpy. So what we can say is that the change in potential energy, or the change in enthalpy, must be negative because we're losing potential energy. And this potential energy is going where? Well, it's actually all being converted into the heat energy that is being lost from the system to the surroundings. Now, how can we say this? Is because of the first law of thermodynamics. We have to conserve energy. We can transform it from one form to another, but overall energy has to be conserved. So the potential energy has to be converted into heat energy. Which, of course, because this system is under constant pressure, the potential energy is really a measurement of the change in enthalpy of the system. Okay? Hopefully you kind of got this idea here because it's really important. Alright, so now what we're going to do is some graphing. we're going to kind of graph and what an endothermic and an exothermic reaction looks like. So I'm actually going to start over on our exothermic side of things. And I'm going to draw some axes, X and Y. And on the Y-axis, I'm actually going to put energy. And energy is increasing in that direction. Now the y-axis isn't so important. The y-axis can be labeled the duration of the reaction. Okay, that's all it is. But IB and AP doesn't really care about labeling the x-axis on these diagrams. Okay, so what's going to happen is we're going to get a curve that looks like this during the course of the reaction. So up here is going to be our starting reactant materials. And down here is going to be the products. Now, we can actually label this as H, potential energy. That might be even better. Okay, so this is looking at kind of the potential energy of a system, not the surroundings of the system. Okay, so looking at this, during the course of the reaction, the reactants, what's happening to the potential energy? Well, the potential energy is going down. So the difference from here to here is the change in enthalpy, or the change in potential energy. And since we're losing potential energy, the enthalpy change needs to be negative. All right? So we're losing potential energy. The delta H, or the enthalpy change, is negative. Where is all that potential energy going? Well, it's being transferred out of our system as heat energy. Okay? And that's also a negative sign because we're losing heat energy. All that potential energy. So this is a great example of an energy diagram for an exothermic process. And I'm actually going to use the first law of thermodynamics and show that the change in heat energy is equal to the change in enthalpy, or potential energy, of the system. All right? So that is an exothermic process. Makes sense? Oops, need to erase that. All right. So let's go to endothermic now. And kind of repeat the same idea. So I'm going to label my axes. Going up is H energy, potential energy, the system. Now, in an endothermic reaction, you're going to get a curve that looks like this. So the reactants and then the products are actually now going to be on top. All right? So what's happening to the potential energy of the system during the reaction? Well, it's going up. All right? So that means the change in potential energy, or the change in enthalpy, since this is a constant pressured system, is going to be positive. Well, where's it getting the potential energy? It can't just create potential energy out of nothing. Well, it's because it's absorbing heat energy from the surrounding environment. Heat energy is going into the system, and that heat energy is being converted or changed into potential energy from the reactants to the products during the course of the duration of the reaction. So what we could say here, using the first law of thermodynamics, is the change in heat energy is equal to the change in the potential energy, or delta H, the enthalpy of the system. All right? Kind of on that outlines or idea there. Now, as terms of stability, okay? We need to look at stability of this overall idea, okay, between endo and exothermic reactions. Which one is more stable of a process? Well, remember back at the beginning of this lecture video, we said that when the potential energy of the system decreases, it creates a more stable system. So because exothermic reactions release potential energy, causing a potential energy decrease in the system, exothermic reactions are more favorable in nature. They produce a lower potential energy system. On the other hand, endothermic reactions is going to increase the potential energy of the system. And so that's just not favorable. Now, endothermic reactions do occur in nature, and that is because there's another component to this whole problem in thermodynamics that we're going to study later that drives endothermic processes and makes so that endothermic processes do occur. It's just that exothermic processes are more favorable because of the idea of lowering that potential energy. All right? So I think I would finish up with just a reminder of that very idea here, as I'm going to write exothermic lowers the potential energy of system. So it's more stable. All right, so that's what I would kind of write down. And on the endothermic side, I would just say that the potential energy is increasing, so the system becomes less stable. And that way, it kind of gives you a reminder note of the importance of potential energy and the stability of a system. All right, so there it is in a nutshell. Enthalpy. Again, one last time to summarize, enthalpy is really the potential energy of the system. The change in enthalpy is the change in potential energy of the system under constant pressure. And as long as you can remember that and remember what happens in an endo and exothermic process, I think you'll be good to go with this. All right, so that is it for this lecture video.